Hi friends, in our last session, we have started with machine tool structure. In that we have studied design criteria for a machine tool structure, that is influence of a material. Okay, so in today's session we are going to continue with our topic. In that we are going to see various variations of V delta and V sigma with respect to L square by H ratio. This is Fazan Kakri and I welcome you all to our lecture series of machine tool design. So let's start. Now, variation of V sigma and V delta with respect to L square by H ratio. So it is very clear that V sigma is the minimum volume required to provide a sufficient strength, whereas V delta is the minimum volume required in order to provide resistance to deformation against deflection, which should be within a specified limit. So as you can see on your screen, a graph is shown. Okay, so on y-axis there is a V, that is a volume. We know we have seen the volume ratio in our last session, VCI upon VMS, right? That is volume of a cast iron upon volume of a mild steel, and that we have obtained, that is 13.07, right? That was indicating that 13.07 times less volume is required in case of a steel beam compared to cast iron. Okay, now on a x-axis there is a L square by H, which means it is a graph of V versus L square by H. Now as you can see, there is a straight line which is shown, that is a linear line, is a representation of a V sigma, whereas the curvature line or a non-linear line is a representation of a V delta. The point at which both this line intersects indicates the optimum value of L square by H ratio and correspondingly optimum value of volume. Okay. Similarly, this is a line for a cast iron. So you can see on a bottom side there is a line shown for a mild steel also, in which you can see a straight line, that is a linear line, is a representation of a V sigma, and a curvature, that is a non-linear line, is a representation for V delta, and the point at which both these lines intersect is the optimum value of L square by H, which is 17.14, and an optimum value of volume that was 1. Okay, so we can clearly say that the optimum volume for a cast iron would be 13.07 and optimum L square by H would be 48, which we have obtained in our last session, right? That is L square by H was 48. Similarly, L square by H for mild steel was 17.14. So you can clearly see over here it is written 17.14, and volume be how much, so corresponding to that it would be 1. For L square by H value less than the optimum value, that is corresponding to the intersection of V sigma and V delta. So this value, optimum value, is this, you can see 48 and 13.07. So in that case, if it is less, then a structure should be designed based on a strength consideration, which means the value of L square by H is within 48, okay, on left side of a curve, then it has to be designed based on strength. While if the value of L square by H is greater than the optimum value, which means greater than 48, then we have to design the structure based on stiffness consideration. Okay guys, so similar is applied in case of a mild steel also. If a design if the value of L square by H is greater than 17.14, that is for case of a mild steel, remember, then we have to design based on stiffness consideration. And if the value, or if we can say if this ratio is less than 17.14, then we need to design based on strength consideration. Okay, now let's proceed further. In practice, the L square by H ratio for a majority of the cases is greater than the optimum value. Hence, it is obvious that we have to design based on stiffness consideration rather than load carrying capacity. So it is a decisive factor for determining the dimension in most of the machine tools. Now next point is that steel structure is lighter, deeper and thinner compared to cast iron structure of equivalent strength. So it is very obvious that lighter, which means we have derived the equation in the last lecture, that is 13 times lighter, right? We have derived that. Similarly, deeper, which means it is larger, how the height is more, that is how much times more, so we can say 2.8 times more compared to a cast iron. And thinner, so how much times thinner, so it was 36 times thinner than a cast iron. So there is a benefit that steel structure, the volume would be quite lesser, right? As you can see in this slide I have written, that is the height of a steel structure would be 2.8 times greater. Similarly, the volume is 13.07 times less, and the thickness would be 36.6 times lesser. So this is the benefit of a steel structure. But we can face certain difficulties if machine tool structure is made from steel. So what are that problems? So we can say the height of machine tool structure is usually limited by other design considerations, which means there is a limitation that up to certain range only we can provide a height of our machine tool structure, because we know several other elements are also present, such as tail stroke, carriage. So it is an important factor, height is an important factor, but in case of a steel structure the height we need to keep higher, right, compared to cast iron. So this is the main problem. Second is small wall thickness in a steel structure requires stiffening ribs. So obviously the steel structure would be thinner, that is 36 times thinner, which means to provide a strength we need to provide a stiffening ribs. Okay, so what this is going to affect? So this is not only going to increase the weight of a steel structure, but also will increase the material cost and a labor cost. So these are the difficulties which we could face if we prepare our machine tool structure based on steel. Okay, now steel should be preferred for a simple heavy loaded structures which are manufactured in a small numbers. So this is a preferred condition where steel has to be used, whereas cast iron should be preferred for a complex structure subjected to normal loading, with these structures are made to be in a large number, which means when we need to prepare the structures in a large number, large quantity, and these structures are subjected to normal loading, then cast iron is much more preferred. Okay, now combined welded and cast structures are also very popular nowadays. So they are generally used where steel structure is economically suitable but we cannot use it, that is it is difficult to manufacture owing to the complexity of some portions, which means we know the problem of a steel structure, that is height is a main problem, and second is the thickness, right? It is quite thinner, 36 times thinner compared to cast iron. So these are the difficulties. So if we want to make our structure economical, so we can do what? So we can combine a welded and a cast iron structure. So it would give a benefit of a steel as well as a benefit of a cast iron. Okay, let's proceed further. Now we need to see material of a machine tool structure. So let us consider a bar which is subjected to a simple tension. So as we know very well that from our Hooke's law, sigma is equal to epsilon E, where sigma is indicating a normal stress, epsilon indicates a strain, and E indicates Young's modulus, right? That is modulus of elasticity. Now can I say that we can express stress in terms of force, right? So it is what? Force upon area, right? So it is written P by A, where P is a tensile force acting on a bar, A is a cross-sectional area of a bar, and we can say epsilon is what? So it is a ratio, that is delta L by L, change in length or elongation upon the length of a material, that is length of a bar. Okay, so you can see L is the length of a bar, okay, and capital E is our Young's modulus. Now the elongation of a bar is given by the expression. So from this equation can we make delta L subject? So it can be written as delta L equals to PL upon AE. Okay. Now over here the quantity P upon delta L. So in this equation, if you see carefully, P upon delta L is going to represent the stiffness of a bar, and it can be written as P by delta L equals to EA by L. So we know that stiffness is a ratio of load to the deflection, right, to the change, or we can say elongation. Okay, so this P by delta L represents a stiffness. We know stiffness is a resistance to deformation, and it is defined as load upon deflection. Okay, so because of this we have written in this way. Now next is for considering a two bars of equal stiffness. So if stiffness is going to remain same, which means for two bars this value is also going to be same, so we can equate the equation. So E1 is Young's modulus for bar 1 into A1, cross sectional area of a bar 1 upon L1, that is length of bar 1, which is equal to E2 A2 by L2, where E2 is a Young's modulus for second bar, A2 is a cross sectional area of a second bar, and L2 is the length of a second bar. Okay, if the bar are of equal length. Now let us consider a condition in that both the bars have same length. So we can say L is equal to L1 is equal to L2. So this equation is going to become E1 A1 is equal to E2 A2. Okay, so it is very clear and it is very easy, right, to understand. Okay, now let's proceed further. So the weight of a bar will be gamma 1 A1L and gamma 2 A2L. Now over here there is a new term, gamma. So what is gamma? So gamma is a specific weight of a bar. Okay. Now what is a specific weight? So whenever a weight is divided by a volume, or we can say for 1 centimeter cube volume, whatever is a weight is called a specific weight. Okay, so that gamma is an indication of a specific weight. So in order to find out weight, we need to multiply this gamma by what? So by multiplying by volume. So A into L is a volume, right? Area into a length is volume. So gamma 1 A1 L is a total weight of a bar 1 and gamma 2 A2L is a weight of a bar 2. Now we need to find out weight ratio. So the ratio of weight will be given by W1 by W2. So the equation will become gamma 1 A1 upon gamma 2 A2. Now since we know that from our previous equation, can I say A1 by A2 will be equal to E2 by E1, right? That is from this equation, as you can see, E1 A1 equals to E2 A2. So from this equation we can write that A1 by A2 is equal to E2 by E1. Okay, now if you see carefully, then in this equation it is going to become E2 by gamma 2 and over here in the denominator E1 by gamma 1. Okay, so E by gamma is a new term which is called a unit stiffness of a material in tension. Okay, so we can clearly say that a weight of a bar, that is this weight of a bar, is inversely proportional to the quantity E by gamma, which is known as a unit stiffness of a material in tension. The larger the unit stiffness of a material, the smaller is the weight of a structure required to ensure that the deflection of a structure due to a particular given load does not exceed the specified limit. So what does this statement indicate? So it is very obvious that larger is a unit stiffness of a material, which means larger is a resistance to deformation of a material. Then we can use a small amount of material, which means a smaller would be the weight of a structure which is required to ensure that deflection does not exceed the specified limit. Okay, so this is what it indicates, that a unit stiffness of material should be as much higher as possible so that we can reduce the weight of a structure, right? Now we have to consider three cases. So let us consider the first case. In that we are taking bar subjected to tensile load. Okay, so let us consider a bar of length capital L subjected to a tensile load, let's say capital P. Now let sigma ultimate be the ultimate strength of the bar material and gamma is its specific weight. Okay, now we have to consider over here factor of safety. So let us say the factor of safety is small n and the area of cross section of a bar will be A is equal to n into P upon sigma ultimate. So it is very obvious that how this equation has arrived. So we know that stress is equal to force upon area, right? Normal stress will be equal to force upon area. So you can clearly see making area subject. So we can write A is equal to n. Now n we need to multiply because it's a factor of safety. Okay, so n into P upon sigma ultimate. Now its volume and weight will be V equals to area into length. So the formula is very obvious. Area will be in centimeter square and length will be in centimeter. Okay, now weight. So weight is what? So we have seen in the previous case that is weight is equal to area into its length, that is volume, into the specific weight. Okay, that is for 1 centimeter cube volume or volume, that is gamma. Okay, so this is the equation of weight AL into gamma. Okay, so we have area formula, we have volume formula, we have weight formula. Okay, so if we compare the weight of two bars of identical length subjected to a tensile load P, so applying the same concept, that is W1 by W2 is equal to, now over here you can clearly see that the formula of our W is AL gamma, right? So what is A? So area formula is NP upon sigma ultimate, right? So over here you can clearly see I have written NP divided by sigma ultimate 1, that is for bar 1. Okay, into what? So into L into gamma. So over here you can see I have written into L into gamma 1. Now remember that over here we are going to consider same load as well as factor of safety would be same, and length is going to remain same, that is both the bars have same length. So in a denominator again you can see it is written NPL gamma 2 upon sigma ultimate 2. So finally the equation will become sigma UT2, that is sigma ultimate 2 upon gamma 2 upon sigma ultimate 1 upon gamma 1. Now what does this sigma upon gamma indicate? So we know that it indicates the unit stiffness. If we compare this equation with this equation, that is Young's modulus E upon gamma. So what does this E by gamma mean? So it was unit stiffness. So similarly over here you can see it is sigma by gamma, which means again it is a unit stiffness of a material in tension. Okay, so let us proceed further. The second case is bar subjected to torsion. Now over here shear force is going to come in picture. There is a twisting moment is given to our rod. Okay, that is our bar. So the shear force in a bar of radius r, length L, and polar moment of inertia IP subjected to torque M is given by this equation. Now you will get confused at how this equation has came. So for clear understanding you can refer over here. I have written one of the formula. So tau by R is equal to T by J is equal to G theta by L, where tau is the shear stress, R is the radius of a shaft. So if you remember this equation you have used in your machine design. Okay, tau by R. So tau we can clearly say torque, R is the radius of a shaft, and T is a twisting moment in Newton meter, where J was what? So J was indicating polar moment of inertia of a shaft. Okay, and what is G? So over here we can say G represents a modulus of rigidity, right? And theta was the angle of twist, if you remember, and L was the length of a shaft, right? So this, from this equation we can resemble this equation. So in our case we are taking tau as it is, R is our radius of the bar. Now twisting moment T over here is represented by capital M. Okay, so twisting moment is represented by capital M, that is our torque, and J, that was a polar moment of inertia, is represented over here by IP. Okay, so you can clearly see now making subject, that is tau as a subject. So this equation will become what? So in general this will become TR by J, right? So compared with this, so yeah, over here we have to write MT, where MT is a torque twisting moment, into R upon IP, where IP is our polar moment of inertia. Now what would be the polar moment of inertia for a rod, that is for a bar? So it would be pi r raised to 4 by 2. Now cancelling out r from a numerator and denominator, we get 2mt upon pi r cube. Now from this equation finally we are going to make r as a subject. Okay, so we can say in the next line you can see, if the shear stress of a bar material is denoted by tau u, that is tau ultimate, and if we take factor of safety small n, then the radius of a bar subjected to the torque mt is found from this equation. So r cube making it subject equals to 2mtn upon pi into tau u. So making r as a subject, we can write r is equal to cube root of 2mtn by pi into 1 upon tau u raised to 1 by 3. Okay, so this is our final equation of a radius of a bar. Now from this radius we need to find out cross sectional area of a bar. So we know what is the equation for area. So pi r square for a bar, that is cross section area is of a circle, right? So pi r square is equal to pi. So entire this term has been written over here raised to the square, whole square. Okay, so the equation finally will become pi in a bracket 2mtn upon pi raised to 2 by 3 in a bracket 1 upon tau u raised to 2 by 3. So this is our equation of area for a bar if it is subjected to a torsion, that is a twisting movement. Now what will be its weight? So we know the formula of weight, it will be equal to AL gamma, where gamma is a specific weight. So area we have found out, this is our equation of area, length L and gamma. So substituting all these values we get final equation pi raised to 1 by 3 in a bracket 2mt n raised to 2 by 3 in a bracket 1 upon tau u raised to 2 by 3 into L gamma. Now obviously our target is finally what? So find out weight ratios, right? So if we compare the weight of two bars of a same length subjected to torque mt, then it follows the following equation, w1 by w2 is equal to, so obviously over here you can see the final equation, if we cancel out all the terms we get 1 upon tau u1 raised to 2 by 3 gamma 1 upon 1 upon tau u2 raised to 2 by 3 gamma 2. In this, obviously we are going to consider that mt is going to remain constant for both the bars, that is twisting moment, torque is remaining same. Okay, length is remaining same, and factor of safety is also remaining same. So the final equation for this weight ratio will become tau u2 raised to 2 by 3 upon gamma 2 upon tau u1 raised to 2 by 3 upon gamma 1. So this quantity tau by gamma, so it's a representation of a unit strength under torsion. Remember that this quantity is an index of the ability of material to resist torsion. Okay, so this has been asked in your exam. You need to keep this derivation in mind and how we need to proceed. So now let us proceed further and see the next type, that is bar subjected to bending moment. Okay, so in this it is very clear we are going to use a bending equation, m by I is equal to sigma by y. So over here in place of y we have placed small r. Okay, now the normal force in a bar of radius r and length l and moment of inertia about a neutral axis is I. The equation is given by this relation. So we are going to make sigma as a subject. It is going to become m by I into r. Now over here, moment of inertia for a bar would be pi r raised to 4 by 2. Okay. Similarly, if we take a case of a polar moment of inertia, so it is equal to Ixx plus Iyy, right? So in a previous case, you have seen that it was pi r raised to 4 upon 2, right? That was Ixx plus Iyy. So over here, it is just I, which means moment of inertia. So it is going to remain pi r raised to 4 by 4. So the final equation will become 4m upon pi r cube, where we can say m is a bending moment in this given section. Now, if a strength of a material is denoted by sigma b, factor of safety by small n, and radius of a bar subjected to bending moment is capital M, then the radius can be found by this relation. So, making r as a subject from this equation, we can say the final equation will become r is equal to cube root of 4mn upon pi into 1 upon sigma b raised to 1 by 3. So, this is the equation of r. We are going to follow the same process. Again, we need to find out a weight ratio, so we need to keep that in mind. Now, the area of cross section A will become pi r square. So pi into this term, right? So r the whole square. So you can see pi in a bracket 4 mn upon pi raised to 2 by 3 into 1 upon sigma b raised to 2 by 3. So is a formula of area. Now what is the formula to find out weight? So weight is equal to AL into gamma. Now multiplying by L and gamma, so the final equation will be pi raised to 1 by 3 in a bracket 4 mn raised to 2 by 3 in a bracket 1 upon sigma b raised to 2 by 3 into L into gamma. This entire equation just multiplying by L and gamma. Okay. Now let's proceed further and determine a weight ratio. So if we compare the weight of two bars of identical length subjected to a bending moment n, then it follows this equation. So we can clearly see W1 by W2 is equal to 1 upon sigma b raised to 2 by 3 into gamma 1 upon 1 upon sigma b raised to 2 by 3 upon into gamma 2. Now how this has came? So we can clearly say that again a bending moment, length and factor of safety is going to remain same for both the bars. So obviously what would be remaining? So sigma b1 and sigma b2. Similarly gamma 1 and gamma 2. So in this case, arranging the terms, we can write it as sigma b2 raised to 2 by 3 upon gamma 2 upon sigma b1 raised to 2 by 3 upon gamma 1. So you can clearly see that this term is inversely proportional to a weight. Okay. So we can say the quantity sigma b raised to 2 by 3 by gamma is an index of ability of a material to resist bending, and it is known as a unit strength under bending condition. Remember, unit strength under bending condition. So higher is this unit strength under bending condition, lesser will be the weight required for a structure. Okay. So this will ultimately reduce the volume of a structure. Okay. So in today's session, we are keeping up till here. In next session, we will continue and we'll start with static stiffness and dynamic stiffness. So till then, stay tuned and thank you all.